Hello, this is Cyprien from FEFO, and today we're up for a new tutorial of Salome Meca with code Aster. So let's open Salome Meca 2018. So I upgraded to the latest release available right now on the website. And what we'll do today is nonlinear contact example. So very classic one called the Hertz contact, and I'll show you from zero how to build the model and how to set up everything that you need to do this analysis into Salome Meca. So now that I open my Salome Meca, let's go into the geometry module where I will just build my geometry. Okay, so how will I build my geometry? So first let's create a few points, right? So point 0, 0, then 1 point on the y-axis at 50, 1 point on the x-axis at 50 as well. Apply. Okay. Yes, I think we are on a good track. Now let's make an arc. Let's make an arc, and let's choose the second method. Choose the center point here and start point. And oh, sorry, I didn't select. Okay. And now, well, you don't see it right now in the model because I just created one arc. But what I want to create is one part like that and another one like that, mirror to this one, and they will enter in contact, both of this. So there will be a surface contact, which is not along all the arc, but only one small portion of that. So I need to create, I need kind of separate this arc into two arcs, right? So how do I do that? Well, first let's create a point, and there is a method here which is very useful called well, it helps you to create a point at the middle or at a certain, you can, if you enter like 0.3 here, for example, your point will be here. If you enter 0.7, it will be here. So I think you got the trick. So I want to have an edge of 45 degrees, so it's just at the middle, so 0.5. And it helps me to construct a point which is at, you can see here the coordinates are a bit complex if I enter them manually, so that's a good way to do that. Okay, and now let's show again the points, and let's build two arcs. So I will not use the first arc. The first arc was just to help me to construct this point. Okay, let's use the first method. Center point here, start point, okay, and the point here. I didn't have to select well. I think there's a small selection problem. Okay, done. Apply. Now let's do it again. 0, start point, okay, and end point here. Okay, so now I have two arcs like that. Now I need also two lines here, one here and one here. So let's start from 0 and let's reach this point here, and again 0 and this point here. Apply. Okay, now I have this. Now let's go into the menu. I can put it in full screen. Let's go into the menu, and there is a build, yeah, here. Build face. Let's build a face. So apply. Okay, now I have my face, and I can do a mirror of this on that. So I'll have to mirror along an edge. So there are two choices here. Either I move this to here, and it will be easy to have the mirror because I already have the axe here, or I could take the point here, extrude it, make a line, and then do a mirror like that. Maybe I'll choose the extrude method because I already have built all these points here. Anyway, you can do any method you want here. So let's kind of activate the vertices that were hidden, and let's use generation extrusion, and I'm gonna extrude the vertex here along x direction. X, okay, didn't choose 0. Vector x. Oh, I didn't choose the right point, right? Okay. Okay, now I have some kind of preview. Well, I don't really need to have the edge so long, but anyway, it doesn't make really any difference here. I'm just using it as a construction tool. Okay, and now that I have that, let's make a mirror of that operation. Transformation, mirror image. And you have several methods here. This is mirror from point. This is mirror axis mirror. I think it's, yeah, this is the one I want to use. Let's select this face here and let's select. Okay, oh, nice. I create a copy. Okay. Okay, now my model is, I think it's almost good to go. Now let's regroup these two faces into one geometric object. So for that we have build compound. Okay, let's build a compound and let's give it a name. Let's call it I don't know, let's be simple, let's call it model, right? Okay, now if you see here, you have my I have my model. Great. Now actually the way you create your geometry also depends the way you want to mesh it. So for my first example, I'll just use a triangular mesh. So my model, my geometry model will be relatively simple. Okay, so I'll just use, I think, this one. So now I need to create some groups for this model. The groups, of course, depend on the boundary condition that I will assign to this model afterwards. So what I will do is that I will block this edge here. So I will block the displacement in x on this edge. I will apply displacement of 2 to this edge here, and displacement of -2 to this other edge here. So let's so the two shapes here will have a contact in this point, and we will see the contact pressure here. Okay, so let's create a group for that. New entity group, create group, select edge. Okay, so I will call those points A1, A2, B1, B2. So A1, maybe A1, B1 maybe. Okay, A1, B1. A1, B1. Add that, apply. This edge here will be, I think you guessed, A2, B2, right? Apply. Those two edges here will be A1, A2, apply. And now I need to add separate groups for those contact areas. This contact area here belongs to the shape 1, so I'll call it contact 1. like that. And this one will be contact 2, cont 2, right? And I think I'm okay for the geometry. I think I won't need more points if I'm not mistaken. So let's go to the next step, which is the meshing part. Okay, so now the geometry is ready. Let's go to the mesh. So let's switch to the S mesh module here. Let's select my model, can activate it again, and let's create a new mesh for it. So to simplify a bit the things, I'll just use the set of hypotheses here of thematic triangulation, and well, I think 11 is a bit too high, so if I'm not mistaken, I think 2 should be okay. So, but of course, let's verify that. Let's compute. Okay, so I think for my first analysis, this will probably be sufficient. You see, nevertheless, that there is a small discrepancy between... Oh no, nothing. I think no, it's okay. It's okay. And now, one thing you should be careful about is that this node here shouldn't be merged with this one. So you should have 2 nodes at the same place in this place. So the way I built my model here, I don't think this node here is merged. So I think it should be okay. But in case you use a different way to construct your model, it may happen that here you get a node which is merged. In which case, well, you have to be careful because you'll have some problems. Okay, so now that I have this, let's create the groups for the mesh, right? Create groups from geometry. Let's select those groups here. Okay. And I think I'm done with the geometry. So with the meshing, I mean. So that was quite quick for this model. So it was pretty simple. So okay, now that I have my mesh, let's go to my Aster Study module, and let's do the simulation. So in the current case, let's add a stage, and you see that those functions become activated. So the first step is always to read a mesh. So let's read my mesh one that I have here, which is automatically imported from the mesh module, so you don't have to export it. And let's call it mesh. Okay. And let's go into modify mesh, and let's use orientation. I think I have to use this one, orientation Po2D. So this is to give an orientation to the contact area here. So that's important to assign an orientation to those 2 contact edges. And by the way, you see that there is a bit of improvement on Salome Meca 2018. Before, you had to be careful about the name here, that it was exactly the same for both. Now you have this automatic option. So when I click OK, you see that the name is automatically set to be the same. So it resolved the kind of problem you had with the previous version, which is very nice, I have to say. Okay, so I read the mesh, I modified it. So next step is to assign a finite element model. So my model here is axisymmetric model. So I have to everywhere. It's a mechanic model, and there is, I think, axis or something. Axis, yep. That's the one we want to use here. Okay, okay, done. Now, okay, now let's define the material. And linear isotropic, edit. And here let's define 200,000 in 0.3. Now my model is in millimeter, but as you see, my Young modulus should be 2 power 11 or something like that. So it should be much higher than this. So why am I choosing a Young's modulus which is lower than the actual real value of steel if I was to use steel? It's because I want to make this model a bit more flexible, so you see what happened in the contact area. If I increase too much the Young modulus, as it would be in reality, this would be simply too stiff here, and we wouldn't get a very nice distribution of the pressure. So that's why I'm using this value. But always be careful about the unit and ask yourself, well, is this unit I'm using the right one? Okay, okay. Now I define the material, but I have to assign it to my model. So let's activate my model and let's assign everywhere the material that I just created here. Done. By the way, don't forget to save your model. So I'll just save it somewhere. Okay, study 1. Let's make a file. Hertz. You never know when we can get some kind of surprise. You know, everything is suddenly deleted. You didn't save your model, and then, well, you understand. You're in very deep trouble. Anyway, let's continue. So material, yeah, it's done. Now, what's the next thing? Boundary condition and loading. Yeah. So let's go and define loading and the constraint of my model. Assign mechanical load. And what I will define everything into one load, but I could separate as well. But anyway, it works like that. So, and it's simpler. So let's do that. Enforce degree of freedom. And let's select the group of elements. So A1, B1, yep. So on this edge, I want to fix the degree of freedom displacement X at 0. Now let's add another one on that group of elements. So A1, B1, I think that's, yeah, that should be this one here. Well, we don't see it because there's the axis, so I think that's what. But the number of elements is 25, so that's correct. dy, and here we want 2 millimeter. Okay, 2. And let's define a third one. Group of elements A2, B2. And here we have -2. Okay, and that's done. And now that we have that, well, of course, we're lacking the contact condition, which is one of the most complex thing in this example, which is the contact, right? So that's why this Hertz contact is a model which is actually used a lot to validate the contact models, because we know mathematically the kind of result you should get. So if you change the mesh, if you refine it, if you use quadratic element, all those kind of things which has an impact on the contact, well, you can have, you know, a very accurate idea of is your model correct or not. Okay, so let's go into so there is in BCN load you have Discrete Contact. So that's what we use to define the contact. And now we see we have several options. So we have discrete, we have continue, and we have other kinds. So this one is simply to fix two parts together. So that's kind of glued contact. And this is for fracture mechanics. So the most simple one is a discrete one. That's not necessarily the best, but that's, let's say, the easiest to converge. And this is a node-to-node contact. So we'll use the discrete one for this to start with. And now we need to define the zone of contact. So in the zone of contact, I'm just inputting the two areas which are in contact. So here it's a bit hidden, but you have actually one is ESC. So you see ESC, it means slave, and this one is master. So you have to be careful which one you choose as the master and which one you choose as the slave. So generally the master is the most rigid one and the slave is the one which has the most curvature. But in this case, well, both are more or less meshed the same size, so it doesn't have really any impact, at least at this point. So I'll just choose the surface 1 for the slave and the surface 2 for the master. And you have different algorithm also. So you can use so this one, stress. Penalization is some kind adding some kind of coefficient to make the contact more easy to converge, but it introduces also more errors, so you'll get less accuracy in the contact area. So I'll just use this one, contrainte, so stress in French. And let's see if I forgot some kind of option. I think that's probably okay for the rest. Okay. And now for the algorithm used, well, I'll use this one, point fixe, which is let's say the most simple one. Not necessarily the best either, but that's generally you start with something simple and then you try more advanced algorithms which are more accurate but also require more calculation power and better mesh to converge. So we'll start with this one, and I think that's all I need for this. Okay, so let's see what we have now. Okay, so now this analysis will be a nonlinear static analysis, so I need also to introduce two things. I need to have a function which is give me the iteration of the number of increments I will divide my load to make the nonlinear calculation, and I need another function which will be a ramp and will be multiplied to the load and will be basically kind of telling the solver that at each increment my load will be multiplied by this ramp function and will be calculated slowly. So it will not apply the load directly at the first step. So that's generally the way used to make this kind of nonlinear static algorithm converge. So let's create first the step. So for that we have to go in, let me think, define list reals, which is real, right? So list R, and we'll get, let's use this, 0. So debut means start. So we'll start at 0. Then we will compute some intervals. So it will end up at 1. And we have to define a certain number of increments. So let's start with a number of 20, for example. if it doesn't converge, you can increase the number of increments. Okay, and let's define the ramp function. So here, define function. And coordinates. So the function at 0, so it's a ramp, so 0, 0, and 1, 1. And if you want a visualization, this is basically what we are getting. So the load at step increment 1 will be multiplied by this value, and increment 2 by this value. So the load will slowly increase to up to it reach the final loading, which is 1. And let's choose the time. So we can call it ramp. That. Okay. And now that I get that, I can finally define analysis here, which is static, which is stat nonlinear. And you see, by the way, that now the types of analysis are separated, so you can see more clearly the dynamics, the statics, and the thermics, and the kind of other types of analysis. So it's kind of nice. I like this new separation. Okay, so now that I have this, let's define that. So the loading, let's give it my load here, and multiplier function will be my ramp function. And let's define the time step list R. Now what do we need more here? Yes, the contact. So contact, don't forget it. And then, yeah, let's use the Newton method. And, well, I don't know if it's required, but I know that sometimes it's best to use this, react. So it means that the matrix will be computed every iteration. And I think this is all I have to set up for this. And now we have to, okay, post processing, we have to define what kind of additional type of result we want, and don't forget to set up to enter the same name than the analysis. So I want the contraint, the stress. I want the stress, and let's define this SIF LNO and SIF NO. Okay, I think it will be okay for now. Well, let me think, maybe I should add also SIF sigma alga, sigma LNO, sigma no maybe. This one, sigma LNO, yeah, I'll use this one. Result, I think the other things are okay. And last thing here is to set the output results, so we're able to read the result with Paravis afterwards. So let's call it hertz.rmed. And don't forget to activate here and add the results. Okay, and I think that's it, so let's save. So now the big moment, launching the calculation, and it usually never works from the first time, so we'll see. Well, you see, by the way, that with this new version, 2018, now you have the dynamic printing of the result here. Oh, and I get a green for the first try. Wow, that's nice. That's nice to see. So I think I'm able to look at the results and see what I have here. Okay, so let's go back here. And the first thing I'll have to do is to create a new group which will be along, so it will be a group of nodes which will follow the contact here in order to get the displacement in this area. So this group, so I have to use the function here, dphi group, and select my mesh, and let's take a look which one it was. Create group, I think it's create group node. Let's take a look at the options, and so group of elements. So let's give it, should be not mistaken, I think take from the master surface. I think I took the one as the master, and I need to give it an option here. This one. This option here. Let's give it a name. That. Okay, and select that again. Okay. Okay, that's it. So this group will be used in order to extract the curvy line coordinate from this. Okay. Now I'll do something that which is actually quite good in Aster Study. Maybe you don't know about it. You can set several stages to kind of uncouple your different analysis, so you don't have to run all of that every time if you want to do some post-processing afterwards. So for that, create a new stage, and I'll set up my functions in this new stage. So you'll see afterwards. Well, basically for the moment it's just like that. I'm just adding a new stage, and what I need to do here is to let's take a look. I think I need to use this option, post releve T, in order to extract from this group information of the pressure. So result here, group of node. So group of nodes. Have to select, I think, this. Yep. Here I have to enter the name of my group that I define here. So my name was this one, node art. And operation I'll do here is extraction. I want to extract the value, the name of the field, I think it's this, and the name of the field I want to extract is, so I extract the sigma, which one was it? Sigma L, no, I think. Sigma L, no. Sigma, where is Sigma L, no? Yep. This one. Okay. One with keyword. Oh, I think I forgot something. Let's see. at least one argument group. No, new must be defined. Okay, I think I forgot this one. Okay, I didn't select this one. Okay, let me think about it. Oh, I think I did a little mistake. Here, this is where I define the group. Yeah, I forgot. So, this is where I have manually to enter this. This name cannot be found here because this group will be created by the solver actually. So when I launch the solver, it will create this group with this name, and then after that, this name will be selected manually in this step. So I have to get this name here. And I think sigma I'll know. Let me think. Oh yeah, so here is what I want to extract. So it's not, I made a small mistake. The field I want to extract from sigma L is the stress in y direction. That's the pressure of contact. So that's what you need to put here. SIYY is the name of the stress field in y direction, which is contained into sigma L. So if you don't know those information, well, you have basically to export those results into a text file and take a look what are the names of the fields that you need to extract. Okay, and I think there is still one thing to do. Time. I need to at which time step I want to extrude. So I will only extrude at time step 1. So when the analysis is finished, that I'm extrude the pressure curve along the axis. Otherwise, it will extrude it at every time step, which is not what I want. Okay. I'm not totally sure it will work from the first try, but I kind of hope it will. So we'll see. So now that I got this table, if I want to print it on the screen, I have to kind of transform the result from this table into a function. So there is something called here Rusu function, which will help me to do that. So this Rusu function takes a table and will transform it into a function. So the function will be SIYY. Sorry, no, this is X. SIYY, and this will be EPS curve. Okay. And the last step will be to print out this into a file. So we'll use imp function to print this into XM Grace format curve. So you need to have this Grace, this kind of software that you need to install. And let's give it a name. Okay, let's Hertz pressure. Save it as a file, and here I will just give it the function. Not this one, this one, from this Rusu function. Okay, time to see if this works. Save. Well, I'm not totally sure to succeed from the first try. This kind of thing is generally difficult. And by the way, those are 2 stages. So you see you have reusable here. So if you want to reuse the first stage and not compute it every time, you have to check this option. And next time you run, you can run only this stage 2. Okay, now let's wait and pray. Green light. Still computing. Oh, okay, and I'm getting green. So I guess it's okay. I just forgot to do one thing, which is to put the curve in interactive, so it will automatically print it out. Otherwise, now it basically printed out as a file, so I have to open the file to show it to you. But if you go in here and you check this option, pilot interactive, you'll basically get it printed out. And that's at the same time give me the opportunity to show you how to run only this stage. So you see this should be blue, so it will not compute it again. And you'll have some kind of fork like that. And I got this printed out. Nice, it works from the first try. Well, that's really the first time I'm getting so lucky, because with all those options, you never know. So you get a lot of errors and you have to correct all this, but here it works great. Okay, so now I'm getting the pressure from this. Now I see that the unit is a bit too large, so I think I have still a small problem somewhere. Probably there is a factor 10 somewhere, so I think I kind of, probably material properties, I added a 0 too much or less. I think it was, but anyway, you get the idea of how you do this. So this is the pressure at the contacts printed out in this curve. And that's it. So, and if you see it very good to have this option, because you don't need to recompute the first step. You can directly compute the second step, and it's much faster. Okay, and that concludes this tutorial. So if you want to get a bit more challenge, well, what I think you should do is to try to mesh that with quadratic elements, and also you can try to mesh them with quad elements and quadratic, and try to kind of play with the different contact algorithm to see what's the impact of the different contacts algorithm used, and what you get as an input, and that will teach you some valuable lessons here. So thank you very much again for watching this video. I hope you learned a lot from it, well, you're welcome to leave some comments on the blog and to let me know what you want to see, and if you have questions, don't hesitate to ask. Thanks again for watching. So if you're on YouTube, you'll probably find the link to the article and the next videos inside the description. Otherwise, you can go on my blog feaforall.com and click in the category open source FEA, and you'll find all the articles I wrote about open source FEA and the previous videos inside this category. So thank you for watching. I hope that you learned a lot, and that you will learn a lot using all the videos that I am sharing on my blog. So if you like those videos, please help me to share them with your friends and other engineers, and also please let me know what you think in the comments. It's always great to have some kind of feedback, and if you have some ideas of things you would like to learn or do with FEA, please also let me know. Thank you for watching again.